Acceleration due to gravity and Newton's second law. So in this lecture, we're going to kind of take a look at what Newton really saw when the apple fell on his head. The focus of this lecture is to calculate A of gravity, acceleration of gravity, and kind of explore the role that Newton's second law plays in all bodies that fall. So, as the story goes, a young Isaac Newton is at college in Cambridge, which is in England. And he's sitting under an apple tree. And that tree actually does exist in Cambridge. I got to see it. Cute little fence. And that was kind of a cool moment for me. But the story goes that an apple fell on Newton's head. And he started to question why apples fall towards the center of the earth and don't move in any direction that they want. And he started to develop laws based on these ideas. And there's three really big ones. Now we've talked about the first one, we've talked about the third one, but now we're going to explore the second law. And the second law deals with this idea of acceleration. And now that we have the language, we can start talking about it. This is what Newton said. The acceleration produced by a net force on an object is directly proportional to the magnitude of that net force and is inversely proportional to the mass of the object. Now that was a language in Newton's day, and it's kind of complex, but can we translate for you for modern speak? What it says is force net equals mass times acceleration. And if you don't want to write all those words, F equals ma. And so basically this is a way of looking at the interaction of forces, masses, and accelerations and how they relate to each other. Now, I've used this PhET demo before in order to help us understand this idea. And so if I look at this simulation, I see that there is a crate here. And I'm told that it has 50 kilograms, which actually is a mass. And currently, the net force, or the sum of the forces, is 0 newtons because there's no forces being pushed to the left or pushed to the right. And so currently, the velocity of the crate is 0. But it remains 0, and so therefore the crate is not accelerating. The net force is 0, and so therefore the acceleration is 0. But I can get this figure to apply a force onto the crate. And currently, this figure is applying 50 newtons of force to the right, but frictional forces are also applying 50 newtons of force to the left, and they're canceling each other out because they're going in opposite directions. And my net force is still 0, and so is my acceleration. I can apply 100 newtons of force, and the situation still holds. But if I apply 150 newtons of force, it overcomes the frictional force and inertia, and now we have a net force of 56 newtons being applied to the right. And we see that the velocity is increasing, so therefore the crate is accelerating. The question is, can we solve for acceleration? And so if I kind of sketch what's happening, I have a surface here and a crate. And in the beginning, I am told that my net force equals 56 newtons. And so that's one of my givens. I am also told that the crate has a mass of 50 kilograms. And that's a given. If I have a force net and a mass, I can figure out acceleration. And that is in meters per second squared. And because Newton's second law says force net equals mass times acceleration, I can start substituting and replacing numbers for letters. So my force net is 56. My mass is 50. And my acceleration I don't know. In order to get acceleration all by itself on the right-hand side, I'm going to do the opposite math function so that 50 cancels with the 50. But whatever I do to the right, I must also do to the left. And when I do this math in the purple circle, purple square, I find that my acceleration equals 1.12 meters per second squared. And once I've done my math, I believe that I see that the crate is accelerating at 1.12 meters per second squared, which is pretty cool. Now, because we're on this simulation, we can do something interesting like remove all of the friction. In this case, all of the force of the figure becomes the complete net force. But here's my question. What happens when the figure is no longer pushing on the crate? The crate is moving. It has a velocity or a speed of 23.4 meters per second, but it's not changing. And so therefore the acceleration is not changing either. And so when you have a constant velocity, that tells you that net force must equal 0. And now let's go back and take a look at what Newton actually said in his law and try and figure it out. Okay, it says acceleration, but here we go, this directly proportional and this inversely proportional. And so this is kind of a new concept. But what Newton's second law says, if there's more net force, there's more acceleration. And so as one thing gets bigger, force, acceleration gets bigger as well. This is what's known as a direct relationship. As one characteristic in the relationship goes up, a different characteristic in the relationship goes up. Hey, if one characteristic goes down, the other one goes down as well. And I like to think of these as field goals. So force has a direct relationship to acceleration. The flip side of that coin is, if I increase the mass, the acceleration has to decrease. And so if I have more mass, I have less acceleration. This is what's known as an inverse relationship. As one characteristic goes up, mass, the other characteristic goes down, acceleration. And they can flop back and forth. These are more like Egyptians, right? As one thing goes up, the other thing goes down. And so Newton's law basically begins to start talking about things that accelerate towards the center of the Earth. And it's been found that things all accelerate at the same rate or acceleration. Now, we have some tools at our disposal known as FNEOMs, and we can calculate the acceleration to gravity if we were able to gather a little information from a YouTube video. These are called How Ridiculous, which is a YouTube channel out of Australia, and basically they smash things with really heavy objects. It's a lot of fun. Check them out.
Okay, first ever hostess slot in 3, 2, 1.
So okay, my kids love this YouTube channel, but I'm a physics teacher. And I'd like to point something out. They're about to drop this incredibly huge, massive piece of metal from a very high place. In the beginning, we can say, because we're physicists, that the fist hangs there for just a split second, so its velocity initial is 0. In the video, they explain that the fist is raised to 40 meters above the sand pit down here. So this fist is 40 meters high, and I've given us a way of looking at time. Now I'm going to play this film full speed, but then I'm going to go back and use a feature of YouTube in which if you hit pause and then you use the period, it will advance the YouTube frame one frame at a time. If you use the comma, it will rewind the YouTube frame one frame at a time.
It's down! Big! Oh, I heard something!
Alright, that happened really, really quickly. Is there any way we could slow down the film so that we could get a very accurate time? And if you see, I have the fist right here in the middle, and I'm going to use the period button to advance the film 1 frame at a time until that fist just barely touches the ground. And right there, I believe that the fist is encountering the ground and crushing a poor dinosaur underneath it. But that took 2.860 seconds for the fist to fall all 40 meters.
Oh, I heard something that did not sound good for Rex. Oh, gently hit Rex. Oh, God. You okay? How's your leg? You okay? Leg all right? Oh,
Don't need legs no more.
Legs gone. What's that?
That was probably that noise.
Yeah, it's never a question of whether he'll live, it's how he'll live. I think he's going to live
We're
well.
living a great life.
Let's watch that slowie of it falling, eh?
So through the course of this video, we found 3 bits of really important given information. We found that the displacement is negative 40 meters. Negative, you ask? I'll explain in a minute. Velocity initial is 0 meters per second because the fist hangs there for just a split second. And then our slow motion camera, or our slow motion film, allowed us to figure out it took 2.860 seconds for the fist to go from the top until it crushed the dinosaur. So in the YouTube clip, we had the ground and then the Hulk fist high up into the air. There are a couple things we were able to extract from our video. Number 1, we figured out that the velocity initial of the Hulk fist is 0 meters per second squared. Meters per second, because for a split second it hangs there. And I call this the Wile E. Coyote effect. At the very tippy top, as something falls, it hangs there for a split second, so we get to say its velocity initial is 0. So that's a given. We also are told that the displacement of the fist in the y-axis is 40 meters. But I'm going to add some more information. It is negative 40 meters, and this is the reason why. When I quickly ask which way is positive, everybody's going to say up. But the fist itself is traveling downward. And so this negative indicates downward motion. And so I have a displacement in the y of negative 40 meters. The last characteristic we got from the film was time. Time was 2.860 seconds. And the whole purpose of this activity is there any way that I could figure out the acceleration? And I'm going to be a little bit more detailed due to this G, or gravity. And so we're trying to figure out what rate things accelerate towards the center of the Earth. And now, if I have a velocity initial, a displacement, a time, and an acceleration, I should be able to pick a FNEOM, or an equation of motion, that's going to help me. And if I do that, I see that displacement equals velocity initial times time plus 0.5 times acceleration times time squared. If I go to replace numbers for letters, my displacement is negative 40, and that equals my velocity initial is 0 times my time, which is 2.860, plus 0.5. I don't know what acceleration is, but I do know time, and that is 2.860, and I have to square it. Now any number times 0 becomes 0. So this blows up. Boom. But I can get out my handy-dandy calculator and I can simplify what is in the purple circle. And when I do that math, I find it is 8.1796. Now, the next step in simplifying is I can multiply 0.5 times this number here. And I find that negative 40 equals 4.0898 times A. In order to get A all by itself on the right-hand side, I'll divide by 4.0898 so that these numbers cancel each other. But whatever I do to the right, I need to do the left as well. Now, if I solve the math in the blue circle, I get a result of negative 9.78 meters per second squared. Which is interesting because we had looked at a negative before and it meant that things are slowing down, but this negative here has a new meaning. Once again, which way is positive? Most people say up. But the thing that we are measuring is accelerating in the downward direction. So it accelerates downward. Or it's going faster and faster down. And so this means that as long as I understand what direction things are going in, I can talk about things accelerating in the downward direction or decelerating in the upward direction.